Hi, I'm Monali,
And I'm Jenny.
and we're going to present our Tetris Solver. So, a large part of AI involves searching for a goal state in a graph or maximizing a utility based on an agent's knowledge base. So, the goal of our project is to create a bot that can beat average human in Tetris. The player's goal in Tetris is to clear as many lines as possible, and therefore, the bot's goal will be to maximize the number of lines cleared. Our version of the game has a few rules. There are 7 main pieces represented by these letters. Each piece can be rotated by 90 degrees, however many times you need. The board is 10 by 22 tiles with 2 rows on top hidden. The pieces stack on top of each other until a piece is stacked above the 22nd row. The pieces are generated using a 7 system random generator, which is basically like choosing from a bag of 7 pieces randomly, and when the bag is empty, it just gets replenished and you continue choosing randomly again. The rate at which the pieces drop remains constant, and the score calculated is the total number of lines cleared.
The bot needs a way to judge the best move, so we chose heuristics that it should take into account. The first heuristic, height added, represents the height added to the total height of the board. The second, lines cleared, represents the total number of lines that any given move clears. The third, holes made, represents the number of holes created by that move, where holes is any empty block on the board with a piece above it. Holes below, which represents the number of holes below a block, and hole height, which represents the distance off the ground to a hole underneath that block. And using all these heuristics, we can create a penalty function, which is just their sum times some weight for that sum. Note that we want to maximize lines cleared, so it will have a negative weight while all others will have a positive penalty. We coded this project in JavaScript using 5 JavaScript files in total and a CSS and HTML combination to display the game. The first 2 JavaScript files were classes that we created to make our game easier to display, a board and an updater. The board represents the game board structure and contains methods to help the gameplay, and the updater is used to make pieces drop and the game continue as though in motion. The second 2 JavaScript files were for our bot, and they're a heuristics file, which was just consisted of several helper functions to calculate the heuristics, and an AI bot file, which actually made the calculation of the best move. The bot considers both the current piece and the next in penalty calculation and recurses back to find the lowest penalty score. And then the final JavaScript file is one main file that just puts all of the other functions together and calls them appropriately so the game can be played.
The bot considers both the current piece and the next piece when searching for the best move by performing a tree search. The edges in the tree represent the penalty for placing a piece at a certain position on the board. The nodes represent the actual position of the piece on the board. The root is the current board without any pieces added. The first layer of nodes in the tree represent all the different positions the current piece can take. The second layer of nodes represent all the positions the next piece can take, based on where the parent node of the current piece is. We wrote a recursive function that performs depth first search to find the min cost path to a leaf node. And once this leaf node is found, we look at the parent node, which points to the current piece, the position of the current piece, and that position is chosen to place the current piece. We use the genetic algorithm to figure out the optimal weights for the heuristic function. We made the range 0 to 500 for the positive weights and negative 500 to 0 for the negative weights, which is for the lines cleared. The fitness function, we generated 100 random weights and random weight vectors and ran the bot 50 times, calculating the average number of lines as the fitness for each random vector. Then we selected 2 of the fittest parents from a random 10%, and for these 2 parents we performed a crossover, which is just a linear combination of the weights, and we did this a total of 30 times. We gave it a mutation, which was basically we gave each child a 5% chance of decreasing or increasing by a value of 10, and Lastly, we replaced 30 of the children with the most unfit 30 parents and repeated the algorithm. And these are our resulting weights. We decided to make a human component for our project. We needed a way to measure the performance of the bot, so we made a human version of the game so we can fairly compare the bot and see if it could actually beat a human. And this human version was needed because it incorporates the rules we established for the bot, so we can't just use any other implementation of Tetris because it needs to play by the rules and the scoring of the same way the bot is made to do.
After adding this human component, we ran the bot 100 times and had 10 different players play 10 times. And we got these results. The human average was 85.9, while our bot's average was 233.2. However, on occasion, the human beat the bot versus human pair up. And because of this, we decided to look into adding more heuristics to our penalty function. So we went ahead and we found two more heuristics that we wanted to add to the bot's performance. The first one is aggregate height, which is just the sum of the height of each column, and this accounts for times when one column is much higher than all others. And the second heuristic we added was flatness, which is just the sum of the absolute value of the change in height between each column. And this just tries to keep an overall flat board so that way you don't have too many columns with different heights. And after adding these heuristics, we reran the genetic algorithm to obtain this new weight vector and get this new penalty function, which we then went on to use.
So as you can see on the left, this is a human version of the Tetris game. And on the right, you have the AI bot. Right now, Jenny is playing the human version. She can, rotate as she needs, go left and right as she needs to clear as many lines as possible. Here you can see the score is written of like how many lines she clears. And the next piece is shown, and if I click this reset button, the whole board will reset. And same thing with the AI bot. We have the score over here, the next piece, and the reset button. And also the AI bot can rotate the pieces just as Jenny can. The pieces are going pretty fast, but that doesn't matter in the context of our project because we're just comparing the score, which is based on number of lines, not time. And as you can see, like it's not afraid of making a hole, and it'll eventually clear the hole by clearing the lines on top. And it's trying to keep the level of the columns relatively flat and avoiding making any random column really high compared to the relatively other ones. And as you can see right now, Jenny has a score of 7, and the bot has already cleared over 100 lines. And yeah, and this will keep on going until this entire board is filled.
As you can see, this has been running for a while, and the score is already above 1700.
Here are the results of the bot with the new heuristics. And as before, the human score averages at about 86, and the bot with the original heuristics was about 233, and the average score of the new bot with the new heuristics is about 6,000, and the highest score we've seen so far is about 24,000. So we can see that the new heuristics helped a lot, and running the genetic algorithm also worked very well to configure the weights.
In conclusion, our bot can beat the average human Tetris, and these methods that we use, graph search and genetic algorithms, can be used for several applications, ranging from a robotic vacuum cleaner searching for dirt to applications in bioinformatics. Thank you for watching, and we hope you enjoyed watching our Tetris Solver.